been thinking a lot about hardware in the last couple of years, and I want to explain some things that I've learned coming from the more ML and data science side. And so before saying like what you need to know about GPUs, I want to like sort of explain why I think there's like a feeling that it must be obvious, that it's obvious. It's like it is like trillions of dollars are getting poured into running workloads on GPUs, and everybody's being asked to run stuff on them. But I want to give like a deeper reason why I think that's the case, and maybe a little bit more appealing to an engineer or a data scientist. So the fundamental thing here is that like latency scaling for compute died sometime in like the Bush administration probably, and GPUs embrace a different paradigm for scaling, bandwidth scaling, and that seems like it might have some more legs. So let me talk you through some of the like history and the kind of high level stuff. So just to remind people what hardware we're talking about here. We're talking about processors. This is basically what a processor is made out of. This is the SUSE 1 computer, a logic gate from it. This was one of the early digital computers, a mechanical computer. And the way it worked was that the like true and false values, Boolean values, were represented by the position of physical components. And then a clock, like a ticking clock with a pendulum and everything, maybe not with a pendulum here, but a ticking clock would push. And then if something was like present, 1, then it would like contact it. And if it wasn't present, 0, then it would push past it. So in this case, like you can get A and B out of such a system by like, if A and B are both true, these two plates move forward and you push it. When the clock ticks, it'll push that plate forward and push all of that forward. So, some things have changed in the last like 90 years on how computers work, but so like we use different physics these days. But fundamentally, this is how the processors work. There's a clock that ticks and sort of pushes stuff around to change the state of bits. So that leads to like a particularly nice form of like making computers go faster, which is just take that clock and speed that clock up, right? Most computing systems have like a pretty limited relationship to real time. So it doesn't matter, like very few programs really care about whether that tick is like a millisecond or a nanosecond. And so you can take them and you can just speed them up. And that was what we did for a very long time. Kind of like the halcyon era of this was the 80s and the 90s when things were like ticked up, the rate at which people could increase the clock rate. And so during that period, you could just wait and then like buy a computer, software would run faster, and like literally the same binary would just run faster. No software engineers involved. And this was really great. And sometime in the early 2000s, the kind of physics that backed this, Dennard scaling, broke down. You couldn't decrease voltage anymore without having too much error, or incurring too much power if you increase the clock rate, and so this sort of flat line. And so this is like a very particular case. It's very like simple and straightforward one, so I like it. But this is also actually kind of like a very generic phenomenon that is has been noted across multiple computing systems. So this is looking at the memory subsystem, the network subsystem, the disk subsystem, the microprocessor, what we were just discussing. Over time, how does bandwidth improve versus latency? And this comes from originally by David Patterson, but this version is from his textbook. And the key thing to pull off this chart is that if the lines all followed that dashed slope there, then latency would improve at the same rate as bandwidth. And this would be nice. There's this principle, a lesser known version of Almbel's law, which is that a computer should have about 1 instruction for each byte of memory, or each bit of bandwidth. And so if computer systems started off nicely balanced, if they follow this behavior, then they're going to become imbalanced, because one of those was latency and the other metric was bandwidth. So that's the first thing to pull off this chart. Things are not along that straight, the line of quality. The other one that is less commonly remarked on with this plot is that actually the slope there is not, it's not that they're just like off the line, like they have the same slope but they're off it. They're actually like, they have a slope of about 2, all of these lines. Classic scaling law thing, like you thought your linear regression plots were bad, but like they're little fast moves. But the like key thing to take out of that is that the like when latency improves by a factor of 2, you should expect bandwidth to improve by a factor of 4. And so this sort of like breakdown of latency scaling happens a lot. And this, these like 2 phenomena, or maybe it's 1 phenomenon, is slowly and inevitably changing like pretty much everything about software. So just like to pick a couple of things, like rise of analytic databases. This is something where there's a lot more opportunity to write something specialized to handle like these like larger queries that are more amenable to bandwidth and less in need of quick latency. I'll talk about a lot of these, or I'll talk about a few of these as we go forward, but in particular, GPU acceleration. But I think once you start thinking about it, you see it everywhere in like the way the computing trends over the last like decade. There's kind of, I'd say there's like 2 basic things that people do to solve this problem. One is to do things in parallel. So the example of like vector processing. So your clock can't go any faster, right? So the clock's going to tick at the same rate. But what if you just did 2 things each time, right? Then you can get twice as much work done. And then you do the clock cycle, right? You have to wait the same amount of time for my fingers to snap. You get 2 snaps in that amount of time. So this means you're doing things in parallel because they're happening at the same time. That's like the important distinction here. And that allows you to get more done, without making anything particularly faster. The other big change is maybe people in the last couple of years have started writing a lot more programs like the one on the right that have this funky new async await keyword pattern in JavaScript or Python or Rust or whatever. And what this does is it takes your program and kind of shreds it into a bunch of smaller programs, little tasks. And then the reason why you need to do this is because when you have something that has like a lot of bandwidth, but also a very high latency, what you have is like a giant pipe that you need to fill. So this is like most clear in networking, so I'm gonna pull that example. So like you wanna send a bit from one side of the country to the other. There's a fundamental limit on that called the speed of light. So if you try and improve if you just like keep focusing on latency, you're gonna hit like a hard physical barrier, unsurmountable according to all known laws of physics. And we're actually like not that far off this. I looked some numbers up and it's like 2/3 of the speed of light, even though you're passing through routers and all this stuff along the way. And you're like bouncing around inside the fiber optic cable. So despite that, still like 2/3 of the speed of light. So there's a limit to how much you can improve that latency. So there's a length there that you can't do anything about. So if you want to get more done, you have to make that pipe bigger. But you have to be able to like send more in any given unit amount of time, increase the bandwidth. But then to like actually fill that pipe to make use of that, it's probably going to cost you more. It's going to be harder to make a gigabyte pipe instead of a megabyte pipe. So now you've got to, if you want to fill that pipe, you're going to need to send more across it. So this can mean like sending, people do lots of things with concurrent programming to fill pipes, but it's like maybe just like aggressively send stuff even if you're not sure that somebody's going to need it. That's the sort of thing you might do. Or just send HD videos because like, you got the space for it. It's maybe not going to cost you more. I guess if you're the one paying for the wires, not that most of us do. But yeah, so like talking about this, GPUs, to like frame how GPUs and CPUs differ, GPUs take both parallelism and concurrency further than CPUs do to maximize bandwidth. So like if you look at the sort of like silicon area of a CPU and a GPU, this is like a highly contended, very optimized resource. So you learn a lot about these systems by looking at where they devote area. So CPUs spend a lot of their very precious silicon area on some like somewhat desperate attempts to cut latency. So have a cache that just like
tries to pretend as though things are like really close to your registers instead of far away in RAM or far away in disk. They have a lot of like control area, like mostly for like taking instructions and shredding them up into tinier pieces to try and get instructions done faster. So like start doing the instruction before you've even asked for it so that it gets done faster. That's where a lot of that silicon area for control actually goes in like an Intel CPU. And then the like business end, the actual computing, is happening in the green part there, the ALUs, the arithmetic and logic units. And those are actually like only a quarter of the space in this diagram. On a GPU, and a lot of that is actually about trying to make those things like go faster, these individual smaller cores, so they can get one specific thing done at a higher rate. GPUs instead kind of like embrace the fact that they're going to have latency, and they spread that latency over as many operations as possible, operating on them in parallel and concurrently. And the way they're able to achieve a much higher bandwidth for arithmetic and logic operations by having a lot more weaker and slower computing components. So to put some numbers on that, because this is the no bullshit data conference, let's compare like a pretty nice server grade CPU, a pretty nice server grade GPU. So on the top is an AMD EPYC 9965, on the bottom an NVIDIA H100, and the AMD EPYC has 192 cores. With hyperthreading, you can run 384 parallel threads. So you're issuing instructions to 384 threads per clock cycle. If you look at an H100, even though there's only 132 like core equivalent streaming multiprocessors, you can actually issue like 100 instructions to 128 threads per clock cycle, one of those, which is pretty cool. So that's like 16,000 threads in parallel, and like a factor of 20 reduction in like watts per thread, which is pretty cool. And you could quibble a little bit with whether you should count vector lanes or not, which might change this to a factor of 10. But it's still a pretty notable difference. So that's parallelism. And then on concurrency, this one is like subtler, but very important. Like, so in theory, you can run as many concurrent threads as your operating system can support on a CPU. Like, there's no special hardware resource that's meaningfully constrained here. Like, things start to get nasty at like millions of threads, but you know, that could be fixed if you really wanted to. So the thing that really kills you is actually context switching. If you want to go from executing one thread to executing another thread, it takes about 1,000 clock cycles, like microseconds. And then it also has like cache dirtying effects. And so substantial can kind of like slow things down even further. On a GPU, these like the context switching, going from issuing instructions in one thread to another, happens literally every clock cycle. That's like one of the prime directives of GPUs is to maintain that, maybe every 2 clock cycles in some architectures. And so that's like nanosecond scale, so a factor of 1,000 faster. So even though like it looks like, oh, only 250,000 threads, what is this, the mid 2010s? But you like, this is like really serious concurrency, like almost parallel, because it changes every clock cycle. Cool. So I'm talking about, like, I wanted to spend a lot of time on this sort of why, because I think it actually reveals a lot of the what that you need to understand about GPUs. That GPUs are this like highly parallel, but also highly concurrent processor. And both of those things are like maximized in the in search of increased bandwidth. And this has managed to avoid some of the same scaling problems that have bedeviled CPUs in the last decade and a half with latency scaling. So there's one like final point for why you should take some of this stuff seriously. It's not, you know, just because your executives manage an AI strategy and like spend a bunch of money on 100s. So like if you think about this latency bandwidth divide, it's like we would expect these curves to keep going. And so you would think that maybe the system that embraces this like quadratic scaling, the bandwidth, is maybe going to be the one that is like going to win. You can hide like a lot of bullshit and inefficiency in like a quadratic over a linear. So even if you have to do something kind of silly or wasteful, if you can do it at in square root, time, like people will maybe be happier. Something of a bitter lesson from the hardware side. Okay, so now like some like more concrete bits and facts about GPUs. So I'm going to these in a bit more for like a particular kind of bandwidth, math bandwidth. So they're good for algorithms with high arithmetic intensity. Specifically specialize in low precision matrix multiplications, which are a type of extremely high bandwidth, or sorry, extremely high arithmetic intensity algorithm. So if you can ride that wave, you'll be doing well. The particular GPUs most people want to program are NVIDIA GPUs, and they're programmed with the CUDA stack, which I'll try and give you a high-level tour of. CUDA, this like software stack, sort of like Linux, it's like this, or POSIX or something, it's like a big thing that you kind of need to know. You don't need to actually write CUDA C++ kernels. You should for the hardware, but you don't actually need to become like a CUDA C++ engineer to be an effective data scientist using this hardware. So I'll talk through the good news on that one at the end to leave us all in a good mood. All right, so GPUs are designed for high arithmetic intensity. So these are the technical specs of that H100 GPU I was just talking about. These are math bandwidths. How many floating point operations can you do per second? The key thing I want to draw your eye to is let's pick the FP4 that says 4 petaflops. There's an asterisk. So divide the number by petaflops. You can do 2 peta, that's a trillion. No, quadrillion, 2 quadrillion operations per second, bonkers. But in order to like have a number to operate on, a number needs to like end up in the registers, right? So the processor is the orange part that I've highlighted there. The numbers are stored usually in the random access memory of the GPU, which is the thing I've highlighted in blue. That memory is soldered on, it's HBM3E, I think, for this GPU, high bandwidth memory. So it has like 3 terabytes a second of bandwidth, which ought to be enough for anybody, but it's less than 2 petaops, right? So of 1,000, right? Anytime you load a number, you want 1,000 times. So that's arithmetic intensity. It's an ops to byte ratio. It's how much do you do with a number once you have loaded it into basically cache or registers. So what this means, like a computer science professor of mine said that all algorithms should be linear and like anything else is too slow. I think that was Mike Jordan. But with GPUs actually, because you're able to parallelize things, you can kind of take these n squared things and make them feel more like n algorithms because you're spreading them out over a lot of hardware. So if you have these like algorithms that are n squared operations for n memory accesses, this hardware can speed them up a lot. So there's like the specific, so like things that work well for this. Matrix multiplication is the most obvious one. So speaking of which, like transformer language model inference works really nicely for this, especially during prompt processing, because the ratios are pretty high. Like you take in a bunch of tokens, you need to load the weights, like from RAM into registers. You need to load all the weights. If it's a mixture of experts model, this is a good idea to do mixture of experts because you don't actually have to load all the weights each time. But you have to load all the weights that you need, pull them in, use them to produce a new token. So especially during the pre-fill stage, which is iteration 1 here, you bring in a bunch of tokens and the same weights get applied to all of those tokens. And so that's a really nice, that's really nice for arithmetic intensity. The ratio is still not great here. This is an 8 billion parameter language model in FP8. This is like rough numbers here. 8 gigabytes go in, you do 64 billion floating point operations. So a ratio of 8 to 1. If you could bring in, if you had a longer context or if you had more prompts, then you would have more floating point operations to do, but you wouldn't really change that number there on the amount of data you need to move. So you would increase that arithmetic intensity ratio. So what this means, somewhat counterintuitively, you can kind of add more prompts or produce more output tokens like for free. So this is why it's nice to run a higher, there's a lot of benefits to running, I guess a larger model would give you more operations maybe, or generating more tokens, multiple tokens per output, like in DeepSeek, or running on multiple user inputs, or generating like 10 responses per user and then picking the best one. So these are all like, as speculative decoding kind of fits in this category as well, places where it's like somewhat counterintuitive that like this additional work basically gets hidden because you're not actually bandwidth on the work you're thinking about, the algorithmic work, but on this like very boring bookkeeping of moving memory around. So that this can work for data analytics. Wanted to talk about this since I think a lot of people have more experience with the analytics type stuff here. So consider like the 1 billion row challenge. This is not a great one for a GPU. You do about 1 operation per aggregate per row in this challenge. So you need to take the minimum, the maximum, and an average, which gives you 2 operations. But that's like, so you're loading a few bytes and then you're doing like a few operations. That's not great. But interestingly, if the 1 billion row challenge was like, oh, and then like also compute an embedding of the city name, or like, and also do like a windowed average and a windowed min and do a windowed maximum, all of a sudden you'd have more things to do with each byte you load. So what this means is like new aggregates are like free. Additional analyses for free. Your business leaders will be excited. They've always thought that they were free, but now they actually kind of are. I think it's a little unclear whether analytic storage engines are exactly the right fit for this. I talked about this with Chong once, who's in here, about like maybe we need like a blockwise thing so you can load and do like a column family looking thing, but he thinks it's not. We're already set with current formats. Your like Parquet, your Lance format, whatever. So maybe that actually just already solves it. There's some work on this already. But yeah, okay, so the latest GPUs are, like, unlike previous GPUs, are a little bit less of a universal math bandwidth machine and a little bit more of a specialized low precision matrix multiply machine, driven by how much money OpenAI and others are giving them. So the latest GPUs are specialized for low precision matrix multiplication. There's a specific unit of the GPU specifically for this. It's called the tensor core. You can see they have a very large silicon area devoted to them, which is a sign they must be pretty important. NVIDIA likes to draw them in this way, which is supposed to imply that like 2 matrices come in and a lot of work comes out, which is a good kind of mental model for them. They have basically hardware level instructions that implement matrix multiplication. Victor over the CISC people over RISC. So these matrix multiplication operations are the one that actually get that super, super high matrix multiplication, or super, super high math bandwidth here. So one, like that's indicated by the use of the word there. And then 2, you'll note that I didn't even highlight the double precision tensor core because that thing is too slow. Like it's not just a factor of 2 slower than regular single precision. It's like, yeah, almost over a factor of 10. But also you'll see that like it goes all the way down to like byte precision. And in the latest Blackwell architectures, it goes down to nibbles, 4-bit. To people, and like it's a little hard to find. Like machine learning is nice. Like neural networks are very vibes based. You can rip out a bunch of bits and they still do basically this. So if you're going to use these things in analytics, you're going to want to kind of come up with ways that you can tolerate reduced precision. I'm unaware of any specific work on this, but the closest thing I could think of in the analytics world would be like sketches. People already use sketch data structures where you tolerate some reduction in precision for your aggregates in exchange for way speedier responses. This is like an Apache Druid or similar databases, probably ClickHouse too. And so you already have this notion due to probabilistic data structures like Bloom filters that you're going to be slightly less precise. So just add the lower precision into your model and your users won't even notice because they're already agreeing to your terms of service that includes getting the answer wrong sometimes. So yeah, that's a potential direction, the sort of thing you should be thinking about, like how can I sort of embrace lower precision in order to take advantage of this very powerful new silicon. Okay. All right, so there are other GPUs also have a similar unit in them, but I was talking really specifically about NVIDIA, have used them this whole time. NVIDIA GPUs are the main ones you're gonna wanna use, and you'll program them with CUDA. NVIDIA GPUs are basically the only game in town, at least for now. If you want like a detailed explanation of why, I would check out this article from Semi-Analysis. Like if you look at just the numbers that the manufacturer reports, it looks like AMD might be a great choice. That will someday be true, perhaps, but the software is not there yet. And so they go into great detail about that. And yeah, quite skilled engineers, so not a skill issue, I would say. So let's talk about some of that software. What is it? What does it do? So the top thing, the thing that probably a lot of people in this room have attempted and failed to install, like myself, is the CUDA and the CUDA C++. It's a multi-layer thing. Your application reaches via libraries like Torch, which has a bunch of CUDA and regular C++ in it, down to talk to this CUDA runtime API, which is this like higher level API for accessing that's your libcudart. At a lower level, CUDA, which is the driver API, that lets you talk to the driver. That part is the thing that lives in the kernel, like NVIDIA.ko on Linux, and that is the thing that actually drives the hardware. So this is your stack here, and this is what maps sort of your applications down onto the actual hardware. So people will call all this CUDA, people will call multiple parts of this the CUDA driver. Things about a CUDA problem, fortunately. Everything is CUDA. The hardware is also CUDA hardware. Anyway, what you are referring to as CUDA is only part of a full system, which I've taken to refer to as CUDA/PTX. Sorry. So CUDA C++, the language, is an implementation of a programming model called the CUDA programming model. This is like an abstract thing, and it's called CUDA. Anyway, so on the left is this programming model. The key thing about it is that it has notions of threads of work and shared memory spaces, and then it talks about how those threads of work are grouped together to run in parallel, how they run concurrently, and how they use memory in order to coordinate. So that's what's going on the left, very directly onto the hardware, which is shown on the right. These things, like especially if you look at a GPU from 5-10 years ago, thing is like. So this is this program and others. So CUDA C++ is what people call a high-level language, like C, which is to say it's not the language of any machine. And it's even like an extra high-level language in that it gets compiled down to a thing called PTEX, parallel thread execution, which is not actually like x86 or ARM. It's not the instruction set for a specific machine. It's an instruction set architecture for an abstract machine. And so this compile a GPU program once and then run it on hardware that didn't even exist when you compiled it, and that behaves possibly very differently in its internals. So this has allowed NVIDIA to do all kinds of crazy things, like go from 32 bits to 64 bits for their like instruction and address formats without anybody changing any code, which is pretty cool. It also gives you back that magical experience of the 90s, where your program literally just runs faster because you paid for a new computer. And so that's kind of the core thing that PTEX does. You can look detail about it. I think won't go into more about it, but you can check it out in the GPU gloss. Speaking of which, a lot of that stuff that I was just sharing is from this GPU glossary that I put together. That's supposed to be sort of CUDA docs for humans, sort of like high-level explanations, lots of interlinking, a bunch of additional resources. So you can find the right forum post or the right PDF that has the answer in it. Okay, so right, conscious of time. I haven't been pulled off the stage yet, so okay, great. So, all right, so that's the CUDA stack, and you do need to learn quite a bit about that in order to operate these effectively. But what you don't necessarily need to do is learn how to do all the stuff that like DeepSeek is doing at the CUDA C++ or PTEX level, or SAS, the assembler level. You don't necessarily need to do that to get the vast majority of the benefits that we've been talking about here, which is great, because I'm hoping to avoid ever needing to seriously learn C++, and I'm hoping that like Rust will just, and then I'll be fine. So writing performant kernels is really fucking hard. So if you want to see a little bit more about this, check out Cy Bain's classic work log on doing matmols on Ampere GPUs at like its state-of-the-art performance. And then check out, after reading that, check out the even more complicated stuff that Pranjal did on the H100 for H100 GPUs on the Hopper architecture. Like the things like the CUDA programming model just get absolutely shredded to pieces by what it takes to actually implement the state-of-the-art performance kernels. Like every abstraction wilts in the face of this amount of scrutiny on performance. Like you have to take the scheduler of your threads into your own hands and do it yourself and not trust the hardware to do it for you, for example. So like somebody needs to do this. But that person doesn't need to be you unless you're like betting the whole company on being the best person at doing this. Part of what a lot of the engineers writing software, like very substantially a software company, it's part of what makes their hardware actually useful. There's a bunch of stuff on here going across a very wide array of like levels. So like when I say like you don't need to learn to write your own CUDA kernels, that's this kernel authoring layer down here. In support of that, you have all these things like, communication libraries. You have slightly higher level kernel authoring libraries like Cutlass. You have things like SDKs at an even higher level, Rapids for data science or data analytics stuff, and frameworks for like, even higher level. I guess you'd call that an SDK. TensorRT and others will like, help you run your code. And there's like quite a lot in here. And this is both like some of the higher levels are mostly about developer productivity and avoiding like the need to like a bunch of stuff. The like lower levels, like Cutlass, for example, is there because like is there less about developer productivity because it's hard to be very productive with Cutlass, no offense, but because like that's actually how NVIDIA achieves themselves the like highest performance out of their hardware. It has a bunch of these like very powerful abstractions for writing performant code. So the good news for anybody like me who's like an ML and data science person is that it's the year of CUDA Python this year at GTC. This was a major theme. A lot of these libraries, like they maybe had like a Python layer that was like somewhat abandoned, or they had Python bindings that were highly unPythonic, but there's been a substantial amount of software development in the last year from NVIDIA and upcoming in the next year to provide higher quality Python APIs, to develop them open source and like more like a contemporary software company and less like a hardware company. And this also is not just like, oh, let's write another high-level Python wrapper that's like for LLMs. It's like, no, they're actually making like core CUDA abstractions available directly in Python. And like if you use Cutlass from Python instead of C++, you get JIT compilation that makes your compile times 2,000 times faster, 200 times faster, which is pretty nice. And they generally have the like prime directive of avoiding sacrificing any performance, what someone might call, not literally, but. So one thing I want to call out about this is, in particular, the like traditional route was you do CUDA C++, you would learn, and then you would discover PTEX, and then you would discover streaming assembler SAS. And the CUDA PTEX layer would be where you'd spend a lot of time. You like write your CUDA C++ thinking about what the PTEX will look like. You look at the PTEX thinking about what the SAS will look like. That was like kind of traditional way of doing it. And PTEX sort of formed this like narrow waist in the middle of this like, this is a big ass ecosystem here. Like, there's got to be some point where things get simpler, and that point used to be this guy right here, where as the like compiler target and the like forward compatibility guarantee. So the interesting thing recently is that the importance of this layer is starting to fade, driven, I think, by two factors. One, tensor cores, pretty hard to program in the PTEX abstract machine, somewhat of a repudiation of the like cleanest CUDA programming model. And so they need a different programming model, maybe more programmer controlled asynchrony being a big part of it. And then two, there's been a lot of improvements in compilers since CUDA and since PTEX originally came out. The work on LLVM, the work on multi-level intermediate representation, MLIR, and so this makes it easier to build a compiler, easier to build an intermediate representation, and like demands a new one. And so this is one of the reasons. I was maybe like first out of the gate on this with Triton, which provides a higher level interface that is like easier to map onto tensor cores as a compiler. This is also something that the folks at Modular have been working on with Mojo and Max. And NVIDIA at GTC announced that they will put out a Python level library similar to this. There's slight differences in the programming model, but they're basically about like working at the level of blocks and tensors instead of at the level of like individual pointers and threads. So, you know, if I were just starting to learn this stuff, I would maybe jump on one of these trains and start learning there, and rather than going too deep on the like CUDA C++ PTEX. Sorry, I want to make a very specific point. Qtile is not just a Python library that's like, oh cool, we have a new Python library. It includes its own intermediate representation, TileIR, that is parallel to PTEX, does not pass through PTEX. So the narrow waist is looking a little thicker, which I'm sure many of us in our 30s and later might be sympathetic to. Okay, so that's the story here. If you want a post-it note size thing to remember about GPUs, they're bandwidth-oriented hardware designed for math bandwidth, which means arithmetic intensity of your algorithms. The algorithm that they rip through the best is a low precision matrix multiplication. It takes some pure, but it can be worth it. The way you program it is with this stack of from NVIDIA and others, mostly NVIDIA, the CUDA stack, but don't get confused and start learning to write fast CUDA kernels immediately, unless that's the sort of thing you do for fun. Great. So in closing, I just want to say, been working on GPUs a lot with this as part of the platform that I work on, Modal. We offer serverless access to GPUs, among other things. Take your Python code and run it in the cloud. We'll give you an H1. You can start running code on an H100 in about 3 seconds. And you only pay for it for the seconds you're running it on instead of making, I don't know, a 500 H100 6-month commitment. And if you want to learn more, check out our founder was on Sean's podcast. It's a great summary of like the vision and the current state of things. And if you're interested in the technical details of how he made this kind of development not suck, check out Eric's previous talk at Data Council 2 years ago on how we sort of rebuilt the Kubernetes and Docker infrastructure to be able to like, you know, do cloud native development, but good. Cool. Thank you very much.